What if I told you that everything you think you know about the universe is just the tip of an unimaginable iceberg? Picture this: somewhere out there, beyond the farthest galaxies we've ever observed, there are places where the laws of physics, as we understand them, simply unravel. Black holes so dense they warp time itself, dimensions folded like origami, and entire universes existing parallel to our own, hidden just beyond the veil of perception. These aren't just ideas from science fiction, they're real possibilities, grounded in the most cutting-edge theories of cosmology and quantum physics. And today, we're going to venture right to the edge of infinity, exploring the mysteries that defy our understanding of reality. Think about the last time you looked up at the night sky and felt that tug of wonder. That's the same curiosity that has driven humanity for centuries to unravel the secrets of the cosmos, to ask the big questions about where we came from and what lies beyond. But here's the thing: the deeper we dig, the more we realize how much we don't know. Black holes, for example, these cosmic monsters don't just swallow light. They might be gateways to other realms, or even the key to understanding the birth of the universe itself. And what about the mind-bending concept of parallel universes? Imagine a reality where every choice you've ever made played out differently, where alternate versions of you are living out infinite possibilities. It sounds like fantasy, but some of the brightest minds in physics believe these ideas could be closer to truth than we ever imagined. This isn't just about abstract theories, it's about reshaping how we see our place in the grand scheme of existence. When we peer into the heart of a black hole or ponder the edges of space-time, we're not just exploring the universe, we're exploring the very limits of human understanding. And that's what makes this journey so thrilling. Over the course of this video, we'll dive into the science behind these cosmic enigmas, unpacking the theories that challenge everything we thought we knew. Along the way, you'll encounter stunning visuals that bring these concepts to life, from the swirling vortices of supermassive black holes to the mind-bending geometry of higher dimensions. By the time we're done, you won't just see the universe differently, you'll feel it. So buckle up. We're about to take a voyage to the farthest reaches of thought, where the fabric of reality bends and the mysteries of existence await. Infinity isn't just a number that keeps going, it's a concept that bends our perception of reality. When we talk about the cosmos, infinity takes on a whole new meaning, stretching beyond math into the very fabric of space and time. Think about it this way: if you could travel in one direction forever, would you eventually loop back to where you started, or would you just keep moving into an endless, uncharted void? That's the puzzle physicists like Stephen Hawking and Brian Greene have wrestled with for decades. Some theories suggest our universe might be like the surface of a giant, cosmic balloon, finite but without edges, where traveling far enough in one direction could bring you back to your starting point. Others argue the universe is truly infinite, expanding without limit into an unimaginable expanse of galaxies, stars, and uncharted mysteries. But how do we even begin to wrap our minds around something so vast? Our brains evolved to understand the world on a human scale: trees, mountains, oceans, not the mind-bending stretches of space-time. That's where simulations and thought experiments come in. Picture a video game where the world appears endless because it generates new terrain as you explore. The universe might work in a similar way, with space itself stretching to create more room as it expands. Or consider the idea of a cosmic hall of mirrors, where light bends in such a way that distant stars are just reflections of closer ones, giving the illusion of infinite space. These aren't just wild guesses, they're tools scientists use to test the boundaries of what infinity might look like. And here's where it gets even stranger. infinity might not be just out there in space, but woven into the very small. Quantum physics hints that even within the tiniest particles, there could be layers upon layers of complexity, like an endless Russian nesting doll. Some theories propose that black holes, those cosmic vacuum cleaners, might not just crush matter into oblivion, but funnel it into other universes or dimensions, creating infinite branches of reality. So when we talk about infinity, we're not just talking about size. We're talking about possibilities, parallel worlds, hidden dimensions, and the very nature of existence itself. This is why infinity isn't just a scientific idea. It's a mirror held up to the limits of human understanding. Every time we think we've grasped it, it slips away, revealing new questions, new mysteries. And that's the beauty of it. Whether the universe is infinite or just unimaginably vast, the search for answers pushes us to think bigger, to imagine the unimaginable. So as we dive deeper into the cosmos, remember, infinity isn't just a destination, it's the journey. The moment when everything began, the Big Bang, is often pictured as a single cataclysmic explosion. But the truth is far more fascinating. Imagine a speck of infinite density, smaller than an atom, containing all the energy and matter that would ever exist in our universe. Then, in a fraction of a second, it expanded faster than the speed of light, stretching space itself like a cosmic balloon. This wasn't just the birth of stars and galaxies. It was the birth of time, of physical laws, of reality as we know it. And yet, the Big Bang wasn't the true beginning. It was more like the first frame of a movie, leaving us with burning questions. What came before? What set it all in motion? One clue lies in the faint afterglow of that primordial event, the cosmic microwave background radiation. This ancient light, still detectable after nearly 14 billion years, is like a snapshot of the universe's infancy. Tiny fluctuations in its pattern reveal the seeds of galaxies, the ripples of quantum chaos frozen in time. But here's where things get even stranger. The universe didn't just expand, it inflated, doubling in size over and over again in less than a blink. Inflation theory explains why space is so smooth on a grand scale, yet filled with the clumps of matter that became stars and planets. Without it, the night sky might be utterly dark, empty of structure. But what if the Big Bang wasn't the only beginning? Some scientists propose a cyclical universe, where expansion eventually reverses into a big crunch, collapsing back into a singularity before rebounding in a new Big Bang, a cosmic heartbeat echoing across eternity. Others whisper of collisions between parallel universes, bubbles of space-time brushing against each other in a vast multiverse. And then there's the quantum realm, where particles flicker in and out of existence, suggesting that even a true nothingness might be unstable, always teetering on the edge of becoming something. These aren't just abstract ideas, they're threads in a tapestry that connects the universe's birth to its ultimate fate. If inflation never stopped in some regions, new universes could be sprouting beyond our horizon, each with different laws of physics. If the Big Bounce is real, our universe might be one in an endless cycle, carrying traces of its predecessors like cosmic DNA. Every discovery, from the spin of distant galaxies to the behavior of subatomic particles, peels back another layer of this mystery. And the deeper we look, the more we realize the story of the universe isn't just about where we came from. It's about where we're going and whether the answers lie in the fabric of space-time itself. Black holes aren't just cosmic vacuums, they're the universe's most enigmatic paradoxes. Picture standing at the edge of a bottomless pit where gravity is so strong, not even light can escape. This boundary, called the event horizon, marks the point of no return. But what happens beyond it? Dive deeper, and you'd encounter the singularity, a point where matter is crushed into infinite density, and the laws of physics as we know them simply break down. It's like a glitch in the fabric of reality, where time and space cease to behave in any familiar way. Now, imagine getting too close. The tidal forces would stretch you like taffy in a process whimsically called spaghettification. Your feet pulled faster than your head until you're torn apart atom by atom. Yet, even in this chaos, black holes aren't entirely destructive. Stephen Hawking shocked the world with his theory that these cosmic monsters slowly leak energy, evaporating over eons through what we now call Hawking radiation. This means black holes aren't eternal. They flicker out, leaving behind a trail of unanswered questions. One of the biggest, the information paradox. If a black hole vanishes, what happens to all the matter and energy it swallowed? Quantum physics says information can't be destroyed, but black holes seem to defy that rule unless the data is somehow encoded in the radiation itself, a puzzle scientists are still untangling. Then there's the groundbreaking image that changed everything. In 2019, the Event Horizon Telescope captured the first ever photo of a black hole's shadow, a fiery ring of light bending around the abyss of Messier 87's supermassive core. This wasn't just a triumph of technology, it was a glimpse into the heart of darkness, confirming predictions Einstein made over a century ago. But the image also raised new mysteries. Why does the ring appear lopsided? Could it hint at hidden structures or even the spin of space-time itself? And perhaps the most tantalizing question of all, are black holes gateways? Some theories suggest that instead of ending at a singularity, matter might be funneled into another universe or emerge as a white hole, a hypothetical cosmic geyser spewing out material. Others propose that black holes could be knots in the fabric of space-time, connecting distant regions like shortcuts through the cosmos. While these ideas sound like science fiction, they're rooted in real math, pushing the boundaries of general relativity and quantum mechanics. What's clear is that black holes are more than just gravitational traps. They're laboratories for the most extreme physics, testing our understanding of reality itself. Every discovery peels back another layer, revealing just how much we still don't know. From their violent births in the collapse of massive stars to their potential role in the universe's fate, black holes remind us that the cosmos is far stranger and far more wondrous than we ever imagined. What if you could step through a doorway and emerge on the other side of the galaxy, or even in another time? That's the promise of wormholes, cosmic shortcuts predicted by Einstein's theory of general relativity. Picture space as a vast sheet of paper folded so two distant points touch. A wormhole would be like tunneling through that fold, bypassing the immense distance between them. It sounds like pure science fiction, but the math suggests these tunnels could exist ripples in space-time where the fabric of reality bends into a bridge. The catch, wormholes, if they exist at all, would be incredibly unstable. Without something to prop them open, they'd collapse faster than a blink, crushing anything inside. That's where exotic matter comes in, a hypothetical substance with negative energy, capable of repelling gravity rather than attracting it. Think of it as cosmic scaffolding, holding the walls of the wormhole apart against the crushing weight of space-time. While we've never observed exotic matter directly, quantum physics hints that it might not be impossible. In labs, scientists have created tiny bursts of negative energy using something called the Casimir effect, where the vacuum of space itself seems to push objects together. Could we one day harness this phenomenon to stabilize a wormhole? It's a long shot, but the idea keeps physicists dreaming. And then there's the wildest possibility of all, wormholes as time machines. If one end of the tunnel were accelerated to near light speed or placed near a black hole's intense gravity, time would slow down there relative to the other end. Step through and you might emerge in the past or future. But before you start planning your trip to ancient Rome, consider the paradoxes. What if you went back and prevented your own birth? The universe might have a way of preventing such contradictions, perhaps by collapsing the wormhole the moment a paradox looms. Or maybe, as some theories suggest, every choice spawns a new timeline, branching into infinite parallel realities where all possibilities play out. The beauty of wormholes isn't just their potential for travel, it's how they challenge our understanding of the cosmos. They force us to grapple with questions about causality, the nature of time, and the very structure of space-time. Whether they are hiding in the quantum foam of the universe or waiting to be engineered by some advanced civilization, wormholes remind us that reality is far stranger than our everyday experience suggests. And that's what makes them so captivating. They're not just tunnels through space, they're invitations to rethink everything we thought we knew. We see galaxies spinning, stars orbiting, and the universe expanding, but none of it makes sense without two invisible giants pulling the strings. Dark matter and dark energy dominate the cosmos, yet they're utterly invisible to our telescopes. Picture this: everything you've ever touched, seen, or known, all the planets, stars, and galaxies, adds up to less than 5% of the universe. The rest is a mystery wrapped in darkness, and it's reshaping our understanding of reality itself. Take dark matter first. In the 1930s, astronomer Fritz Zwicky noticed something bizarre about galaxy clusters. They were moving too fast. The visible matter couldn't possibly hold them together with gravity alone. It was like watching a carousel spin wildly with no one pushing it, the only explanation. An unseen mass, something with gravity but no light. Today we call it dark matter, and its fingerprints are everywhere. Galaxies rotate as if gripped by invisible hands. Light bends around empty patches of space, a phenomenon called gravitational lensing. Even the cosmic web, the vast structure of the universe, couldn't exist without dark matter's gravitational scaffolding. But here's the twist: after decades of searching, we still don't know what it is. Is it a sea of undiscovered particles, like WIMP weakly interacting massive particles floating through space? Or could it be primordial black holes, remnants of the Big Bang lurking in the shadows? Experiments deep underground, like the Large Hadron Collider, are hunting for clues, smashing particles together in hopes of creating dark matter in the lab. Meanwhile, telescopes scan the skies for gamma-ray flashes or other traces of dark matter annihilations. Every null result narrows the possibilities, inching us closer to an answer that could redefine physics. Then there's dark energy, the far stranger force. In the late 1990s, astronomers studying distant supernova made a shocking discovery. The universe isn't just expanding, it's accelerating. Something is stretching space itself apart, overpowering gravity. That something is dark energy, and it makes up about 70% of the universe. Unlike dark matter, which clumps and pulls, dark energy seems uniform and repulsive, woven into the fabric of space-time. Some theories suggest it's the energy of empty space itself, quantum fluctuations bubbling in the void. Others propose it's a new kind of field, like the Higgs boson, but with cosmic consequences. What's clear is that dark energy holds the fate of the universe. If it strengthens over time, it could tear galaxies apart in a big rip. If it weakens, gravity might regain control, collapsing everything back into a singularity. Or maybe it's constant, leading to a slow, cold fade as stars burn out and space stretches into infinite emptiness. Together, dark matter and dark energy are the ultimate cosmic puzzles, invisible, enigmatic, and utterly transformative. Solving them wouldn't just fill in gaps in our textbooks, it could overturn our understanding of gravity, quantum physics, and the very nature of existence. Every observation, every experiment brings us closer to peeling back the veil on the dark universe, and when we do, the cosmos might look stranger and more magnificent than we ever dreamed. Parallel universes sound like the stuff of wild imagination, but the math behind them is startlingly real. Imagine a frothing ocean of cosmic bubbles, each one a self-contained universe with its own unique laws of physics. Some might have stronger gravity, making stars burn out in seconds. Others could be so warped that time flows backward. This isn't just speculation, it's a natural extension of inflation theory, the same framework that explains our universe's rapid expansion after the Big Bang. If space can stretch once, why not endlessly, birthing countless pocket realities in an ever-growing multiverse? Then there's the many worlds interpretation of quantum mechanics, where every decision you make spawns a new universe. Choose tea over coffee this morning. Somewhere out there, another version of you did the opposite. This idea comes from the bizarre behavior of particles, which exist in multiple states at once until observed. Instead of collapsing into one outcome, the theory suggests all possibilities play out just in branching timelines we can't see. It's like flipping a coin. In our world, it lands heads. In another, tails, but neither outcome is more real than the other. The implications are dizzying. If the multiverse exists, there could be versions of history where dinosaurs never went extinct, where humans never evolved, or where you became an astronaut instead of watching this video. But here's the catch. These alternate realities would be forever out of reach, separated by impassable cosmic horizons. Even light from those universes couldn't reach us, making them as untouchable as a reflection in a shattered mirror. Yet scientists aren't just relying on theory. Some hunt for physical evidence, like odd patterns in the cosmic microwave background that might reveal collisions between our universe and another. Others simulate multiverse scenarios in supercomputers, testing how different physical constants would affect the formation of stars and life. The results: even slight tweaks to gravity or the strength of atoms often render universes sterile, suggesting our existence might hinge on an improbable cosmic lottery win. Philosophically, the multiverse forces us to confront profound questions. If infinite versions of us exist, does any single choice truly matter? Or is free will just an illusion, with every path already walked somewhere in the vastness of reality? Some argue the multiverse demotes our significance. Others see it as the ultimate celebration of possibility, where every dream and nightmare plays out in some corner of existence. What's clear is this: whether the multiverse is real or not, the idea stretches our minds to the breaking point. It challenges us to think bigger, to question what's truly unique about our universe, and to wonder, if we're not alone in the cosmos, could we also not be alone in the grand tapestry of all possible realities? Time might feel like an unshakable constant, an ever-flowing river carrying us from past to future, but physics tells a far stranger story. Imagine standing near a black hole where gravity warps time so severely that a single minute for you could stretch into years for someone back on Earth. This isn't science fiction, it's Einstein's theory of relativity in action. Time isn't rigid or universal. It bends, stretches, and even slows down depending on where you are and how fast you're moving. The ticking of a clock on a speeding satellite measurably lags behind one on the ground, a phenomenon GPS satellites must account for to keep our maps accurate. So if time is this malleable, what does that say about its true nature? Dive deeper, and the puzzle only grows more perplexing. In the quantum realm, particles don't seem to care about our neat division of past and present. Experiments suggest that particles can become entangled across time, with measurements made now affecting outcomes that already happened in the past. This retrocausality turns our intuitive understanding of cause and effect on its head. Some physicists argue that time might not even be a fundamental feature of the universe, just an illusion emerging from the way we perceive change, like a movie reel creating the illusion of motion from still frames. Think of it this way: the universe might be a vast, unchanging block where past, present, and future all exist simultaneously. Our brains, trapped in this slice of now, stitch together a narrative that feels like progression. Then there's the arrow of time, the stubborn fact that we remember the past but not the future. Why does time seem to move in one direction? The answer might lie in entropy, the universe's tendency toward disorder. A shattered glass doesn't reassemble itself because entropy increases over time, creating an asymmetry between past and future. But here's the twist: the laws of physics themselves don't dictate a direction for time. Run them backward and they still work perfectly. So why does time feel so irreversible? Some speculate that the Big Bang set the initial low entropy state, like winding up a cosmic clock, and we're just riding the wave of its unraveling. The most mind-bending possibility of all: closed time-like curves, paths through space-time that loop back on themselves, allowing time travel to the past without breaking any physical laws. General relativity permits these loops, though they'd require exotic conditions like wormholes or infinite cosmic strings. But even if they exist, paradoxes loom. Step on a butterfly in the past, and could you erase your own future? Some theories sidestep this with self-consistent loops, where any time travel was always part of history, or with branching timelines that avoid contradictions altogether. What does all this mean for free will? If the future is already out there, waiting in the block universe, are our choices just illusions? Or does quantum uncertainty leave room for genuine agency? Philosophers and physicists have wrestled with this for centuries, but one thing's certain: time's fluidity challenges everything we assume about reality. Whether it's an emergent illusion, a cosmic dimension, or something stranger still, time remains one of the universe's greatest enigmas, a mystery woven into the fabric of existence itself. And as we peer closer, we might find that the edge of time isn't a boundary at all, but a doorway to deeper truths about the nature of reality. Einstein famously dismissed quantum entanglement as spooky action at a distance, but this bizarre phenomenon is now one of the most rigorously tested facts in physics. Picture two particles born together like twins sharing an invisible bond. Separate them by galaxies, and measuring one instantly determines the state of the other, no matter how far apart they are. This isn't just theoretical. Experiments have confirmed it again and again. In 2017, Chinese scientists sent entangled photons from a satellite to ground stations over 700 miles apart, and the particles still behaved as if connected by an unseen thread. The kicker: this happens faster than light, seemingly breaking the universe's speed limit. So how does it work? At the quantum level, particles don't have definite properties until measured. They exist in a haze of probabilities, a superposition of all possible states. But when entangled particles are observed, their fates snap into sync instantaneously, as if flipping a coin on opposite sides of the universe and always getting heads and tails in perfect opposition. This defies our classical intuition, where objects need some signal, a phone call, a light beam to communicate. Entanglement suggests a deeper layer of reality, where space and distance might be illusions, and everything is fundamentally interconnected. Could we harness this for faster-than-light communication? Sadly, no. While the correlation between entangled particles is instantaneous, we can't control the outcome of measurements to send messages. It's like having two magic dice that always show matching numbers, but no way to choose which number appears. Yet, this very weirdness is revolutionizing technology. Quantum computers use entanglement to perform calculations at speeds impossible for classical machines, solving problems like drug discovery or climate modeling in minutes instead of millennia. And quantum cryptography exploits entanglement to create unhackable communication. Any eavesdropper would disturb the delicate quantum link, alerting the sender instantly. The implications go even deeper. Some interpretations suggest entanglement hints at a holographic universe, where our 3D reality is a projection of information encoded on a distant 2D surface. Others propose it's evidence of multiple dimensions or a cosmic web linking all things. Whatever the truth, entanglement forces us to confront a startling idea. The universe isn't just stranger than we imagine, it's stranger than we can imagine. And as we peer further into the quantum fog, we might find that the very fabric of reality is woven with threads we're only beginning to untangle. String theory doesn't just tweak our understanding of the universe, it rewrites it from the ground up. Imagine zooming in on an electron so far that instead of a tiny dot, you see a microscopic loop of energy vibrating like a guitar string. That's the heart of this radical idea. Every particle in existence isn't a point but a one-dimensional string, and the way it vibrates determines whether it becomes an electron, a quark, or even a photon. This elegant twist could solve one of physics' biggest headaches, the feud between quantum mechanics and gravity. In the quantum world, particles flicker in and out of existence, but gravity, as described by Einstein, treats space as a smooth fabric. These two frameworks refuse to play nice until strings enter the picture. Their vibrations naturally include a particle that mediates gravity, the graviton, stitching the two theories together like threads in a cosmic tapestry. But there's a catch: strings need room to wiggle, a lot of room. Instead of the 4 dimensions we know, 3 of space, 1 of time, string theory demands 10 or even 11. Where are these extra dimensions? Think of a garden hose. From afar, it looks like a simple line, but up close, it's a cylinder with a hidden circular dimension curled up tight. The universe might work the same way, with 6 or 7 dimensions coiled into shapes so tiny, we'd need a microscope 1 billion times sharper than any we've built to see them. These shapes, called Calabi-Yau manifolds, resemble intricate origami, their folds dictating how strings vibrate and, by extension, the laws of physics in our visible universe. Change the folds and you'd rewrite reality itself: stronger gravity, different particles, even alternate forces. Then there's the holographic principle, a spin-off idea that's just as mind-bending. What if our 3-dimensional universe is actually a projection of information stored on a 2-dimensional surface, like a cosmic DVD encoding a 3D movie? Black holes hint at this possibility. Their entropy suggests information isn't lost inside but smeared across their event horizons. String theory's most daring offshoot, M-theory, takes it further, proposing that our universe might be a membrane, or brain, floating in a higher dimensional space, occasionally colliding with others to trigger big bangs. Picture soap bubbles bumping in a sink, each one a universe with its own physics. Yet for all its beauty, string theory faces fierce criticism. After 50 years, it still hasn't produced a single testable prediction. Without experiments to confirm it, some argue it's more philosophy than science, a dazzling mathematical castle in the air. Others counter that gravity waves, black hole thermodynamics, and even quantum entanglement were once deemed untestable too. Maybe future breakthroughs, like detecting tiny strings in particle collisions or spotting imprints of extra dimensions in the cosmic microwave background, will tip the scales. Love it or hate it, string theory pushes the boundaries of imagination. It dares us to think bigger, to see the universe not as a collection of particles, but as a symphony of vibrating strings, where every note is a star, a planet, or a law of physics. Whether it's the final answer or just a stepping stone, one thing's certain: the quest to unify reality is far from over, and that's what makes science and the cosmos so thrilling. What if the world around us, the stars, the planets, even your own hands, is nothing more than an elaborate illusion? The holographic principle dares to suggest exactly that. Our three-dimensional reality might be a projection, like a movie playing on the surface of an unimaginably distant cosmic screen. The idea sounds like science fiction, but it emerges from one of the most perplexing puzzles in physics: what happens to information that falls into a black hole? In the 1970s, physicist Jacob Bekenstein made a startling discovery. Black holes have entropy, a measure of disorder. This implied they must also contain information, scrambled beyond recognition but not destroyed. Decades later, Stephen Hawking showed that black holes slowly evaporate, leaving behind only thermal radiation. But here's the paradox: if that radiation carries no information, the original data would be lost forever, violating quantum mechanics' core rule that information can never vanish. The solution: the information isn't inside the black hole. It's smeared across its event horizon, like a cosmic hard drive encoding every detail of what fell in. This realization birthed the holographic principle. The universe might store all its data on a two-dimensional boundary, with our 3D existence unfolding as a holographic projection of that data. The math behind this gets even wilder. Take the add S/CFT correspondence, a groundbreaking idea from string theory. It proposes a perfect duality, a universe with gravity in 5 dimensions like ours, plus one extra can be exactly described by a quantum field theory without gravity on its 4-dimensional boundary. It's like discovering that a novel and its movie adaptation contain the same story, just told in completely different languages. If true, this means the true source code of reality could reside on a distant, lower-dimensional surface, with everything we see and feel being a rendered output. But how could this possibly work? Think of a credit card hologram, a flat sticker that creates a 3D image when tilted. In a similar way, the universe's information might be compressed into Planck-sized pixels on a cosmic horizon, with interactions between these pixels generating the depth and complexity we perceive. Even time and space could be emergent properties, not fundamental. Picture a crowd of people forming a wave at a stadium. The wave isn't a thing itself, but a pattern arising from countless individual actions. Space-time might be the same, an illusion forged from deeper, more abstract relationships. The implications are staggering. If the holographic principle holds, it would mean the universe is fundamentally information theoretic, a cosmic computation where matter and energy are secondary to the bits and codes underlying them. It challenges our most basic assumptions about locality and causality. Why should two particles know to entangle across vast distances unless they're reflections of something deeper? And it raises profound philosophical questions. If reality is a projection, what's projecting it? Is there a surface somewhere humming with the data that constructs our lives? Critics argue the principle remains untested, a beautiful idea without empirical teeth. Yet experiments like the holometer at Fermilab have hunted for pixelation in spacetime itself, searching for faint jitters that might betray its digital nature. Others look for anomalies in high-energy particle collisions or quantum gravity effects that could hint at hidden dimensions. While definitive proof remains elusive, the holographic principle has already reshaped how we think about black holes, quantum gravity, and the nature of existence itself. At its core, this isn't just about physics, it's about perception. The holographic principle forces us to confront the possibility that reality is far stranger, far more interconnected than our senses suggest. Whether the universe is a hologram or not, the idea stretches our minds to the very edge of comprehension, revealing just how much mystery still lies at the heart of everything. Cosmic inflation was the universe's most dramatic growth spurt, an explosive expansion that stretched space itself faster than the speed of light in the first sliver of a second after the Big Bang. Picture a tiny speck, smaller than an atom, suddenly inflating to the size of a grapefruit, then a city, then a galaxy, all within a heartbeat. This wasn't just rapid growth, it was exponential, doubling in size over and over again in intervals as short as a trillionth of a trillionth of a trillionth of a second. But why? The leading theory points to a mysterious field called the inflaton, a kind of cosmic energy that permeated the early universe like an invisible fuel. As this field decayed, it released energy that drove space apart with unimaginable force, smoothing out wrinkles and setting the stage for the universe we see today. The evidence for inflation is etched into the cosmos itself. Look at the cosmic microwave background, the afterglow of the Big Bang, and you'll find it's almost perfectly uniform, with temperature variations no greater than 1 part in 100,000. Without inflation, this uniformity would be impossible. Regions of space now billions of light years apart were once close enough to exchange heat, but inflation stretched them beyond each other's horizons, locking in that smoothness like a snapshot. Then there's the large-scale structure of the universe, galaxies clustered into vast filaments and voids, a cosmic web that traces back to quantum fluctuations magnified by inflation. Those tiny ripples in the fabric of spacetime were stretched to astronomical scales, becoming the seeds for stars, galaxies, and everything we see around us. But the smoking gun for inflation might still be out there: primordial gravitational waves. These ripples in spacetime, generated during inflation's violent expansion, should have left a faint imprint on the cosmic microwave background, a swirling pattern called B-mode polarization. In 2014, the BICEP 2 experiment thought they'd spotted it, but the signal turned out to be cosmic dust. The hunt continues, with next-generation telescopes like the Simons Observatory scanning the skies for this elusive whisper from the dawn of time. Finding it would confirm inflation and open a window into energies 1 trillion times higher than anything we can recreate in particle colliders. Yet mysteries remain. What triggered inflation in the first place, and why did it stop? Some theories suggest it was a phase transition, like water freezing into ice, releasing latent energy as the universe cooled. Others propose that inflation never truly ended, that our universe is just one bubble in an eternally inflating multiverse, where new bubbles nucleate endlessly, each with its own physics. And then there's the question of what came before. Inflation erases any traces of its prehistory, like a cosmic reset button, leaving us to wonder if time itself had a beginning, or if our universe is just one chapter in an infinite cycle. What's certain is that inflation wasn't just a quirk of the early universe, it was the sculptor that shaped reality. Without it, the cosmos might be a chaotic, clumped mess, or worse, entirely empty. It set the stage for gravity to pull matter into galaxies, for stars to ignite, and for the delicate balance of physical constants that made life possible. Inflation is the unsung hero of cosmic history, the brief but transformative moment that turned quantum chaos into the ordered universe we call home. And as we peer deeper into its echoes, we're not just uncovering the past, we're decoding the very blueprint of existence. The night sky is filled with 100 billion galaxies, each home to hundreds of billions of stars. So where is everybody? That's the haunting question at the heart of the Fermi Paradox, the glaring contradiction between the high probability of alien civilizations and the eerie silence of the cosmos. Even if life is extraordinarily rare, the sheer scale of the universe suggests we shouldn't be alone. And yet, after decades of searching, we've found no signals, no artifacts, no evidence that anything else is out there. So what's going on? One way to grapple with this is through the Drake equation, a formula that estimates the number of detectable civilizations in our galaxy. It considers factors like the rate of star formation, the fraction of stars with planets, and the odds of life emerging on those planets. Plug in optimistic numbers, and the equation suggests the Milky Way could be buzzing with thousands of advanced societies. But here's the catch: we don't know the true values for most of these variables. For all we know, the step from simple life to intelligent, spacefaring civilizations might be vanishingly rare. This is the idea behind the Great Filter, a hypothetical barrier so extreme that it prevents most life from progressing beyond a certain point, the terrifying possibility. We might not have passed it yet. If the filter lies ahead of us, say, in the form of self-destructive technology or an unavoidable cosmic catastrophe, it could explain why the galaxy feels so empty. Then there's the zoo hypothesis, the notion that advanced civilizations are deliberately avoiding us, treating Earth like a nature preserve or a lab experiment. It's a chilling thought. What if we're being observed but not contacted, like ants in an interstellar terrarium? Others suggest that alien societies might communicate in ways we can't yet perceive, using neutrino beams or quantum entanglement instead of radio waves. Or perhaps they've transcended physical form entirely, uploading their consciousness into vast digital networks, leaving no trace for us to detect. Despite the silence, the search continues. SETI, the search for extraterrestrial intelligence, scans the skies for artificial signals, while missions like the James Webb Space Telescope hunt for biosignatures on distant exoplanets. Recent discoveries have revealed thousands of worlds in the habitable zones of their stars, some with conditions eerily similar to Earth. But even if life is common, intelligence might be a fluke, a fragile spark in a universe that favors microbes over mathematicians. The Fermi Paradox isn't just a scientific puzzle, it's a mirror. It forces us to confront our own fragility, our place in the cosmic story. Are we the first chapter or the last? A statistical inevitability or a cosmic accident? Until we find answers, the stars will keep their secrets, and we'll keep wondering if we're alone in the dark. What if everything you see, touch, and experience is nothing more than lines of code in an unfathomably advanced simulation? The idea might sound straight out of a sci-fi movie, but it's a serious hypothesis debated by physicists and philosophers alike. Elon Musk famously claimed the odds we're living in base reality are 1 billion to 1, arguing that any civilization reaching technological maturity would inevitably create simulations indistinguishable from reality, and statistically, we're more likely to be one of those simulations than the original universe. But is there any actual evidence, or is this just modern solipsism wrapped in tech jargon? Let's start with the science. Some researchers point to the strange behavior of quantum particles as potential glitches in the system. Take the double-slit experiment. Particles behave like waves when unobserved but snap into definite positions the moment they're measured, as if the universe is optimizing processing power by only rendering details when needed. Then there's the pixelation of spacetime itself. At the smallest scales, space isn't smooth but grainy, with a fundamental unit called the Planck length. Could this be the resolution limit of our simulation, the smallest pixel the universe can render? Even the speed of light might be a built-in processing constraint, a cosmic frame rate preventing the system from overloading. But the simulation hypothesis isn't just about physics, it's a philosophical labyrinth. If we are living in a simulation, who's running it? Future humans. alien civilizations, and why some suggest it's a historical recreation, a way for advanced beings to study their ancestors. Others propose it's a form of entertainment or even an ethical experiment, testing how consciousness evolves under different conditions. The most unsettling possibility: we're not the main program at all, but background noise in someone else's simulation, like NPCs in a vast cosmic game. Critics, of course, aren't convinced. They argue the simulation hypothesis is unfalsifiable, a clever thought experiment with no way to prove or disprove it. After all, any evidence we find could just be part of the simulation's design. Some physicists counter that if the universe is a simulation, it would require unimaginable computational power, raising the question, what's simulating the simulators? And if reality is virtual, why do we experience pain, boredom, or the mundane details of daily life? Wouldn't the architect streamline the experience? Yet the debate pushes us to confront deeper questions about consciousness and existence. If we someday create hyper-realistic simulations populated with self-aware beings, would that make our own reality more or less likely to be simulated? The line between creator and creation blurs, leaving us to wonder, is the universe a cold, mechanical place, or the product of something, or someone beyond our comprehension? Whether the simulation hypothesis is true or not, it forces us to look at reality with fresh eyes, questioning the very fabric of what we call real. And in that questioning, we might just find clues to the greatest mystery of all, what it truly means to exist. Black holes devour everything in their path, but what if the universe had cosmic fountains, gushing matter and energy back into existence? That's the tantalizing idea behind white holes, the theoretical opposites of black holes. While black holes trap even light behind an event horizon, white holes would violently repel anything trying to enter, spewing out material like an unstoppable geyser. The math is shockingly elegant. Einstein's equations for general relativity are symmetrical, meaning if black holes exist, white holes shouldn't just be possible, they should be inevitable. Flip a black hole's gravitational collapse in reverse, and you've got a white hole's explosive rebirth. But here's the catch: white holes defy everything we know about thermodynamics. Black holes form when massive stars collapse, a process we've observed. White holes, on the other hand, would need to emerge from nothingness, violating the second law of thermodynamics by decreasing entropy. Think of a shattered glass spontaneously reassembling. It's so improbable that most physicists dismiss white holes as mathematical ghosts, solutions to equations with no physical counterpart. Yet some daring theories suggest they might be real, hiding in plain sight. One wild possibility: the Big Bang itself could have been a white hole event. Instead of a singularity exploding from nothing, imagine it as the white hole end of a black hole from another universe. This idea, called the black hole cosmology hypothesis, paints our entire universe as the interior of a white hole birthed from a parent cosmos's collapsed star. It's a cosmic Russian doll where every black hole in our universe might spawn a new one inside it, a fractal multiverse of nested realities. Then there's the wormhole connection. Some solutions to Einstein's equations hint that black holes and white holes could be linked by an Einstein-Rosen bridge, a tunnel through space-time. Fall into a black hole, and you might be vomited out a white hole elsewhere in space or time. It's the ultimate shortcut, but there's a problem. These wormholes are wildly unstable, pinching shut faster than anything could traverse them. Unless, that is, you have exotic matter to prop them open, a hypothetical substance with negative energy that could defy gravity's crushing grip. So why haven't we seen white holes if they're out there? For starters, they'd be staggeringly rare. A white hole's explosive nature means it would burn out quickly, like a firework in the cosmic dark. Others argue they might disguise themselves as gamma-ray bursts, those blinding flashes of energy we've detected from distant galaxies. Or perhaps they're hiding in the early universe's chaos, their light redshifted beyond recognition by billions of years of cosmic expansion. The beauty of white holes isn't just their strangeness, it's how they stretch our understanding of physics. They force us to ask whether time's arrow can reverse, whether information truly vanishes in black holes, and whether the universe might recycle itself in an endless loop of collapse and rebirth. Until we find proof, they remain one of cosmology's most enchanting what-ifs, a reminder that the universe's deepest mysteries might lurk not in the darkness, but in the blinding light of the impossible. Neutron stars are nature's ultimate alchemist, stellar corpses so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. Picture crushing the entire mass of our sun into a sphere no wider than Manhattan, where gravity is strong enough to bend light into a halo and atoms are squeezed into a sea of pure neutrons. These cosmic diamonds are born from the fiery death throes of massive stars, when a supernova explosion blasts away the outer layers, leaving behind a core so compressed it defies the very laws of everyday physics. But neutron stars aren't just exotic curiosities, they're cosmic powerhouses, spinning at dizzying speeds and wielding magnetic fields trillions of times stronger than Earth's. Take pulsars, for example, the universe's precision lighthouses. As a neutron star rotates, beams of radiation shoot from its magnetic poles, sweeping across space like a celestial strobe light. Some spin hundreds of times per second, flashing with such regularity that astronomers once mistook them for signals from intelligent life. Then there are magnetars, the rarest and most violent breed. Imagine a magnetic field so intense it could strip the data from your credit card halfway across the solar system. These monsters occasionally unleash Starquake's colossal ruptures in their crust that release flares of gamma rays bright enough to outshine entire galaxies for a heartbeat. But the real magic happens when two neutron stars spiral toward each other in a deadly dance. As they collide, the tidal forces rip them apart in a cataclysm called a kilonova, an explosion so energetic it forges the heaviest elements in the universe. Gold, platinum, uranium, the very atoms in your jewelry or smartphone were likely born in such a collision billions of years ago. In 2017, scientists witnessed this cosmic smithing firsthand when gravitational waves from a neutron star merger reached Earth. Telescopes around the world swiveled to catch the aftermath, revealing a glowing cloud rich with precious metals. It was proof that the universe doesn't just destroy, it recycles, transforming the ashes of dead stars into the building blocks of new worlds. What's even more astonishing is how fleeting these events are. A kilonova's fireworks fade in days, leaving behind either a heavier neutron star or, if the combined mass is too great, a black hole. Yet in that brief moment, temperatures soar to trillions of degrees, and conditions mimic those of the Big Bang itself. It's a reminder that the universe's most extraordinary creations often arise from its most violent ends. From the gold in ancient crowns to the uranium-fueling nuclear reactors, we're literally made of stardust, the remnants of celestial giants that lived fast, died young, and left behind a legacy written in atomic ink. Neutron stars challenge our understanding of matter, gravity, and the limits of physical law. They're laboratories for the impossible, where quantum physics and relativity collide in ways we're still struggling to comprehend. Whether as pulsars keeping cosmic time, magnetars bending space-time with their fury, or kilonovas seeding the cosmos with precious metals, these stellar zombies remind us that even in death, stars shape the universe in ways we're only beginning to uncover. And somewhere out there, another collision is brewing, a silent countdown to the next cosmic rebirth. Somewhere out there, hidden behind the thick veil of stars and dust in our own Milky Way, lurks a cosmic enigma so powerful it's tugging entire galaxies, including ours, toward it at over 1,000,000 miles per hour. Astronomers call it the Great Attractor, and despite decades of searching, its true nature remains one of the universe's most tantalizing secrets. Imagine throwing a ball into the air, only to watch it curve sideways instead of falling back down. That's essentially what's happening on a galactic scale, as thousands of galaxies, including our local group, are being pulled toward an invisible gravitational anchor in the constellation Centaurus. The first clues emerged in the 1970s when astronomers mapping the cosmic microwave background noticed something odd. Our galaxy wasn't just drifting aimlessly, it was racing towards something unseen. Later studies revealed that hundreds of other galaxies were caught in the same mysterious flow, like leaves swept up in a hidden river. But when scientists trained their telescopes in that direction, they hit a wall, literally. The Great Attractor lies directly behind the Milky Way's dusty zone of avoidance, a region so clogged with interstellar debris that visible light can't penetrate it. It's like trying to spot a lighthouse through a sandstorm. So what could be pulling us with such irresistible force? One leading theory points to the Norma cluster, a dense gathering of galaxies about 250 million light-years away, sitting at the heart of a larger supercluster called Laniakea, Hawaiian for immeasurable heaven. This cosmic metropolis, containing the mass of 100,000 Milky Ways, might be the primary source of the Great Attractor's gravity. But here's the puzzle. Even Laniakea's colossal weight doesn't fully account for the observed motion. Some researchers suspect dark matter, the invisible glue holding galaxies together, might be clumped in unexpected ways, creating a gravitational hotspot beyond what visible matter can explain. Others wonder if our models of cosmic expansion need tweaking, or if there's an even larger structure further out, pulling both us and the Great Attractor itself. The hunt for answers has pushed technology to its limits. Infrared and radio telescopes, which can peer through dust, have revealed hints of massive galaxy clusters hidden in the zone of avoidance. Meanwhile, sophisticated simulations trace the intricate web of dark matter filaments that might be funneling galaxies toward this cosmic nexus. But the deeper we look, the stranger it gets. Recent observations suggest the Great Attractor might not be the final destination. Our galactic journey could be part of an even grander flow toward an unimaginably vast structure called the Shapley supercluster, nearly 1 billion light-years away. What makes the Great Attractor so captivating isn't just its mystery, it's the humbling reminder that even in an age of space telescopes and supercomputers, the universe keeps its deepest secrets hidden in plain sight. Every time we think we've mapped the cosmos, it throws us a curveball, revealing just how much lies beyond our sight and understanding. Whether it's dark matter, hidden galaxies, or something even more extraordinary, one thing's certain: the universe is far richer, far weirder, and far more alive with motion than we ever imagined. And somewhere beyond that curtain of dust, the Great Attractor waits, silently reshaping the fate of everything around it. The universe as we know it balances on a knife's edge, not just in space, but in the very fabric of reality itself. Hidden beneath the surface of existence lies a cosmic tightrope walk, the Higgs field, an invisible energy blanket that gives particles their mass. Without it, electrons would zip through atoms at light speed, chemistry would collapse, and life as we understand it would be impossible. But what if this field isn't as stable as we think? Enter vacuum decay, a theoretical doomsday scenario where the Higgs field could suddenly drop to a lower energy state, rewriting the rules of physics in an expanding wave of annihilation. Picture a bubble forming in a pot of superheated water. In this analogy, our universe is the water seemingly calm but actually in a false vacuum, a state that appears stable but isn't the lowest possible energy configuration. Quantum fluctuations could, in theory, create a tiny bubble where the Higgs field collapses to its true, lower energy state. The moment that bubble forms, the laws of physics inside it change instantly. The bubble's walls would expand outward at nearly the speed of light, transforming everything in their path. Stars, planets, even the very atoms in your body would unravel as fundamental forces like electromagnetism and the strong nuclear force reconfigure. By the time you saw the wall coming, it would already be too late. There'd be no warning, no escape, just an instantaneous rewrite of reality itself. The math behind this isn't science fiction. Nobel laureate Frank Wilczek and others have calculated that our universe's current vacuum state might indeed be metastable, like a pencil balanced on its tip, seemingly stable until the slightest nudge sends it crashing down. The trigger could be as random as a quantum tunneling event, where the Higgs field spontaneously falls into a lower energy valley. Cosmic rays or high-energy particle collisions might also, in theory, provide the necessary kick. The reassuring part, the odds of this happening in any given year are astronomically low. Estimates suggest it's less likely than a spontaneous asteroid impact wiping out civilization. But unlikely doesn't mean impossible, and that's what makes physicists pause. What's truly mind-bending is the scale of such an event. Unlike a supernova or gamma-ray burst, vacuum decay wouldn't just destroy Earth or the Milky Way. It would propagate indefinitely, potentially rewriting the entire observable universe. There'd be no outside to observe it, no survivors to mourn. The new physics inside the bubble might not even allow for anything resembling matter as we know it. Some theories suggest a post-decay universe could be a cold, empty void where atoms can't form, or a chaotic realm where particles interact in ways beyond our imagination. Yet this terrifying possibility has a silver lining. It forces us to confront how delicately tuned our universe's constants are. The Higgs field's current value sits in a precarious sweet spot, just strong enough to allow atoms and galaxies to exist, but possibly not the absolute lowest energy state. If vacuum decay is a real, if remote, threat, it underscores how little we understand about the fundamental nature of reality. Are we living in a cosmic accident, a temporary configuration that could vanish in an instant? Or is there some deeper mechanism, a law we haven't discovered yet, that stabilizes the vacuum indefinitely? Experiments at the Large Hadron Collider continue probing the Higgs boson's properties, searching for clues about the field's stability. Meanwhile, astrophysicists scan the cosmos for any signs of bubbles that might have already begun expanding from distant regions. So far, the universe seems reassuringly intact, but the very fact that vacuum decay is a plausible discussion in physics departments tells us something profound. The edge of infinity isn't just a place of wonder, it's a frontier where the universe's deepest rules hang in the balance. And that uncertainty, as unsettling as it is, reminds us why we keep looking. Time crystals sound like something straight out of a sci-fi novel, matter that doesn't just exist in space, but dances to the rhythm of time itself. Unlike ordinary crystals, where atoms arrange themselves in repeating patterns like a diamond's lattice, time crystals have a structure that cycles periodically in time, flipping between states without any energy input. Imagine a clock that ticks forever without winding, or a pendulum that swings indefinitely without any push. That's the bizarre beauty of these quantum oddities, first theorized by Nobel laureate Frank Wilczek in 2012, and later brought to life in labs using chains of ions or diamond defects chilled to near absolute zero. The magic lies in how they cheat thermodynamics. Normally, perpetual motion is impossible. Energy gets lost to friction, and systems settle into equilibrium. But time crystals don't violate these laws, they sidestep them. By existing in a quantum system pumped with just the right amount of energy, they enter a state where their structure repeats in time, like a hall of mirrors reflecting not just space but moments. It's as if the universe handed them a free pass to wiggle forever, so long as they don't actually do anything useful with that motion. What's truly groundbreaking is how they redefine stability. In a world where everything tends toward disorder, time crystals are islands of order that persist without decaying. Think of them as cosmic metronomes, ticking in perfect sync even when the rest of the universe marches toward entropy. This isn't just theoretical eye candy, it could reshape technology. Quantum computers, which rely on fragile states prone to collapsing, might one day use time crystals as error-resistant memory, preserving information against the chaos of the microscopic world. Or imagine energy storage systems that exploit these perpetual cycles, though we're still far from turning that dream into reality. Yet the biggest puzzle isn't how they work, it's what they reveal about the fabric of reality. Time crystals force us to rethink symmetry, a cornerstone of physics. The universe loves symmetry, from the spiral of galaxies to the equations governing particles. But time crystals break time symmetry, behaving differently at different moments even when the underlying rules don't change. It's like finding a wheel that spins clockwise at noon and counterclockwise at midnight for no apparent reason. This oddity hints at hidden layers in the laws of nature, waiting to be uncovered. From theory to lab to future tech, time crystals are a testament to how the strangest ideas in physics often unlock the deepest truths. They remind us that the universe still holds surprises not just in the distant cosmos, but in the quiet hum of atoms here on Earth. And as we probe further, who knows what other impossible-seeming wonders might be waiting just beyond the edge of our understanding. The Boltzmann brain paradox is one of the most unsettling thought experiments in physics, a puzzle that makes you question whether anything you know is real. Imagine you're floating alone in the void of space, your thoughts, memories, and even the sensation of your body suddenly popping into existence out of pure random chance. No birth, no parents, no universe, just you, an isolated mind conjured by a freak quantum fluctuation in an otherwise lifeless cosmos. This isn't some dystopian sci-fi plot. It's a legitimate possibility raised by the laws of thermodynamics in an infinite, eternal universe. Here's how it works. In any system, even complete chaos has tiny moments of order, like a gust of wind arranging leaves into a perfect spiral, or a shattered vase spontaneously reassembling for a split second. These fluctuations are vanishingly rare, but given enough time, they will happen. Now, scale that up to the universe. If space and time stretch on forever, there's a non-zero chance that atoms could randomly assemble into a fully functioning brain, complete with fabricated memories of a past that never existed. And statistically, in an infinite cosmos, these Boltzmann brains would outnumber real, evolved minds by an unimaginable margin. So why aren't you one of them? The paradox forces us to confront two equally jarring conclusions. Either the universe isn't infinite and eternal, making Boltzmann brains impossibly rare, or our entire experience is an illusion, a fleeting ripple in an ocean of entropy. Some cosmologists argue this is evidence against certain models of eternal inflation, where pocket universes bubble up endlessly. If Boltzmann brains dominate, why don't we observe a universe teeming with them instead of the stable, ordered reality we see? Others suggest the paradox reveals a flaw in how we interpret probability itself. Maybe consciousness isn't something that can emerge from random noise, no matter how long you wait. Philosophically, the debate spirals into questions about solipsism, the idea that only one's mind is sure to exist. If you can't prove you're not a Boltzmann brain, how can you trust any of your perceptions? Scientists counter that the consistency of the laws of physics, the fossil record, and even the shared experiences of billions of humans make the Boltzmann scenario absurdly unlikely. But unlikely doesn't mean impossible, and that's what keeps physicists up at night. At its core, the Boltzmann brain paradox isn't just about physics, it's a mirror held up to the limits of human knowledge. It asks how much we can truly understand about reality when our tools of observation might themselves be illusions. Whether a quirk of math or a profound truth, it reminds us that the universe's deepest mysteries often lie not in the stars, but in the nature of existence itself. And that's a puzzle with no easy answers. What if death isn't the end, but just a doorway to another version of reality where you're still alive? That's the radical premise of quantum immortality, a thought experiment that twists the many worlds interpretation of quantum mechanics into something deeply personal. Picture Schrödinger's infamous cat, simultaneously alive and dead until someone opens the box. Now replace the cat with you. In a multiverse where every possible outcome plays out, your consciousness might only experience the timelines where you survive, no matter how improbable. It's not about living forever in one universe, it's about always finding yourself in the branch where you didn't die. This idea takes root in a grim hypothetical called quantum suicide. Imagine a gun rigged to a quantum trigger with a 50% chance of firing each time you pull it. In most universes, you'd die instantly, but in a tiny fraction, the gun miraculously jams every single time. Proponents argue your consciousness would only perceive those rare worlds, creating the illusion of invincibility. Of course, no one's volunteering to test this, but the logic echoes in everyday close calls. That time you narrowly avoided a car crash. In another universe you didn't, but you aren't there to experience it, yet the implications are thornier than they seem. If quantum immortality holds, why do we observe anyone dying at all? Shouldn't hospitals be filled with unkillable patients surviving against all odds? Critics point out that consciousness isn't a spotlight hopping between realities, it's a process rooted in a physical brain, which can't magically persist after fatal damage. Others argue the theory conflates perception with existence. Just because you don't experience death doesn't mean it doesn't happen to you in most branches of reality. Ethically, the idea is a minefield. If death becomes an illusion, does life lose its value? Would reckless behavior surge if people believed they couldn't truly die? And what about aging? Quantum immortality doesn't promise youth, just survival. You might find yourself alone in a nursing home at 120, watching everyone else fade away while you linger, trapped by the math of probability. At its core, quantum immortality forces us to confront the nature of self. Are we a single thread in the cosmic tapestry, or a pattern woven across countless realities? Whether a profound truth or a philosophical dead end, it reminds us that the multiverse isn't just about alternate histories, it's about the fragile, fleeting nature of the one life we know we have. And that, perhaps, is the most haunting thought of all. Late one summer night in 1977, a radio telescope at Ohio State University's Big Ear Observatory picked up something extraordinary, a burst of radio waves so powerful and peculiar that astronomer Jerry R. Amon circled the data on the printout and scribbled, "Wow," in the margin. That simple exclamation gave the signal its name, but the mystery behind it has haunted scientists ever since. For 72 seconds, the signal blared at a frequency of 1420 MHz, a band where cosmic noise is minimal, and where theorists had speculated an intelligent civilization might transmit. It was 30 times louder than the background static, matched no known celestial object, and then it vanished. No repeat, no explanation, just a fleeting call from the void that seemed to whisper, "Someone's out there." Decades later, the WOW signal remains the closest thing we've ever had to a potential alien hello. But what was it? The leading natural explanation points to hydrogen clouds or comets, yet none were found along that precise line of sight. The signal's narrow frequency range is also suspiciously artificial. Natural cosmic static usually smears across multiple bands, not a single clean spike. Then there's the kicker. The Big Ear telescope used 2 feed horns to scan the sky minutes apart. If the signal were earthly interference, a passing satellite or military transmission, both horns should have caught it. Only one did, suggesting the source turned off abruptly or moved beyond detection in those 90 seconds. The allure of the WOW signal isn't just its mystery, it's the tantalizing what-if. Imagine a civilization far older than ours, beaming a deliberate signal across the stars, not knowing if anyone would hear it. Or perhaps it was a cosmic accident, a burst from a dying star's technology, or a misaligned interstellar beacon sweeping past Earth like a lighthouse beam in the dark. The signal's brevity plays tricks on us too. Had it lasted longer, we might have triangulated its origin. Had it been weaker, we'd have dismissed it as noise. Instead, it sits perfectly on the edge of plausibility, a Rorschach test for our hopes and skepticism. Efforts to solve the puzzle have only deepened its intrigue. In 2017, researchers scanned the same region with the cutting-edge Allen telescope array, hunting for repeats, silence. Other astronomers proposed a pair of passing comets as culprits, but their hydrogen emissions didn't quite match the signal's profile. Even if it was natural, the WOW signal defies easy categorization, a cosmic one-hit wonder that refuses an encore. What makes this 45-year-old blip endure in our collective imagination? It's the same reason we scan the skies for pulsars or decode distant exoplanet atmospheres, the longing to know we're not alone. The WOW signal is more than data. It's a story we tell ourselves about curiosity and connection. In a universe that's overwhelmingly vast and silent, it's the closest we've come to hearing a voice in the dark. And whether it was aliens, a quirk of physics, or something stranger still, its legacy is undeniable, proof that sometimes the most profound questions come not with answers, but with a single, electrifying wow. In October 2017, astronomers spotted something streaking through our solar system that shouldn't have been there, a mysterious object moving so fast it couldn't possibly be tied to the sun's gravity. Named Oumuamua Hawaiian for Scout, it was the first confirmed visitor from another star, and it brought with it a puzzle that still divides scientists today. At first glance, it seemed like a simple interstellar rock, but the closer researchers looked, the stranger it became. Unlike typical comets, it lacked the glowing coma of gas and dust that forms when ice vaporizes in sunlight. Yet it wasn't quite an asteroid either, showing none of the familiar mineral signatures. And then there was its shape, long and thin, like a cosmic cigar or a pancake tumbling end over end through space, a form almost never seen in natural celestial bodies. But the real shock came when Oumuamua did something utterly unexpected. It accelerated. As it raced away from the sun, it picked up speed in a way that couldn't be explained by gravity alone. Comets sometimes get a boost from outgassing jets of material erupting as they warm, but no such activity was detected. This left scientists scrambling. Some proposed exotic explanations, like hydrogen ice sublimating invisibly, or even the pressure of sunlight pushing on an object as thin as a sail. Others, like Harvard astronomer Avi Loeb, raised a more provocative idea. Could Oumuamua have been artificial? A derelict solar sail from an alien civilization, perhaps, or a probe sent to study our system? The debate raged because Oumuamua defied every category we've built to understand cosmic objects. Its acceleration was subtle but undeniable, like a car easing forward without anyone pressing the gas. The lack of visible outgassing made it an outlier, and its shape, estimated to be up to 10 times longer than it was wide, was unlike anything seen in our solar system. Even its reflectivity was odd, shimmering with a metallic sheen that suggested a surface unlike typical space-weathered rock. What makes Oumuamua so fascinating isn't just its mystery, it's the door it kicked open. Before this, interstellar objects were thought to be rare, drifting through the void unnoticed. Now we know they're passing through all the time. In 2019, a second visitor, the comet Borisov, arrived, behaving much more like expected. But Oumuamua remains the wild card, the one that got away before we could study it properly. Future telescopes, like the Vera Rubin Observatory, will scan for more of these nomads, poised to catch the next one before it vanishes into the dark. The lesson of Oumuamua isn't just about one strange object, it's about humility. The universe is far weirder than our textbooks suggest, and every time we think we've got it figured out, something comes along to remind us how much we still don't know. Whether it was a fragment of an alien world, a shard of exotic ice, or something even more extraordinary, Oumuamua was a glimpse into the uncharted. And the next visitor, it might rewrite the rules all over again. Imagine harnessing all the energy that falls on Earth from the sun, every ray of sunlight, every gust of wind, every drop of rain, and multiplying it by a factor of billions. That's the dream behind the Kardashev Scale, a cosmic yardstick that measures civilizations not by their art or politics, but by raw energy mastery. Proposed by Soviet astronomer Nikolai Kardashev in 1964, this scale divides intelligent life into 3 types, each representing a leap in power so vast it reshapes what's possible. A Type I civilization controls all the energy of its home planet. Type Roman 2 commands the output of its star, and Type Roman 3, it reigns over an entire galaxy, wielding power beyond our wildest science fiction. Right now, humanity hovers around Type 0.7. We're still burning fossil fuels and squabbling over scraps, barely tapping into the sunlight that bathes our world. To reach Type I, we'd need to harness every watt of solar energy, geothermal heat, and tidal force Earth can offer. Picture a world where solar panels blanket deserts, orbital mirrors beam power to the night side, and fusion reactors mimic the sun's fire. But the real game changer, Dyson spheres, megastructures that encase stars to capture their full energy output. Freeman Dyson imagined these as vast swarms of solar collectors, not solid shells, orbiting close enough to siphon a star's fury. For a Type Roman 2 civilization, this isn't sci-fi. It's survival, the only way to fuel interstellar ambitions. Then there's the ultimate leap, Type Roman 3, where energy isn't just harvested but orchestrated across light years. Think star engines, colossal devices like the Cyclical thruster, which uses a star's own light as propulsion, nudging entire solar systems across the galaxy. Or Matryoshka brains, nested Dyson spheres hosting supercomputers the size of planetary orbits, running simulations so vast they dwarf human history. The scale doesn't stop there. Some theorists speculate about Type Roman 4 universal, or even Type V multiversal civilizations, but these stretch into realms where physics as we know it might break down entirely. The Kardashev Scale isn't just about energy, it's a mirror. It forces us to confront our fragility, how easily war, climate collapse, or stagnation could trap us at Type 0 forever. But it's also a beacon, a roadmap to what we might become if we navigate the next few centuries wisely, because the universe doesn't care if we reach for the stars. It simply waits, offering infinite energy to those bold enough to take it. What if life on Earth didn't actually begin here? The theory of Panspermia dares to suggest that our biological origins might lie not in some primordial soup, but in the icy depths of space. Imagine a comet loaded with organic molecules crashing into our young planet billions of years ago, seeding the oceans with the building blocks of life. It's a radical idea, but the evidence is mounting. Take extremophiles, those hardy microbes thriving in places once thought uninhabitable, boiling hydrothermal vents, acidic lakes, even the vacuum of space. Tardigrades, for instance, can survive extreme radiation and dehydration, reviving after years in suspended animation. If these organisms can endure the harshness of space, could their ancestors have hitched a ride on a meteorite? Then there's the smoking gun organic compounds found inside meteorites. The Murchison meteorite, which fell in Australia in 1969, contained amino acids, the very ingredients of proteins. Even more intriguing, some of these molecules were chiral, meaning they had a specific handedness, just like the molecules that make up life on Earth. This isn't random chemistry. It's a tantalizing hint that the raw materials for life might be scattered across the cosmos, waiting for the right conditions to spark into existence. But the wildest twist directed Panspermia the idea that life wasn't just randomly transported, but intentionally sent. Nobel-winning chemist Francis Crick, co-discoverer of DNA's structure, once speculated that an advanced civilization could have deliberately seeded Earth with microbial life. While it sounds like a wild conspiracy, the premise isn't entirely implausible. If a civilization wanted to spread life, microbes encased in protective material could survive interstellar journeys, riding comets like cosmic arcs. If Panspermia is true, the implications are staggering. Life wouldn't be a rare accident but a cosmic inevitability, flourishing wherever conditions allow. It would mean the difference between a lonely universe and one teeming with life, all connected by the same genetic ancestry. And if life spread so easily, intelligence might not be unique either. Civilizations could share not just the same chemistry, but the same origins, making us all distant relatives in a vast, interconnected family tree. The search for answers is driving missions like Europa Clipper and Mars Sample Return, hunting for signs of extraterrestrial microbes. Whether Panspermia holds up or not, it forces us to rethink our place in the universe. Are we Earth's children or the descendants of ancient stardust? The answer might be written in the genes of every living thing waiting to be decoded. General relativity paints the cosmos on a grand scale, planets orbiting stars, black holes warping space-time, while quantum mechanics rules the subatomic realm where particles flicker in and out of existence. Yet when these two titans collide, the universe breaks. Picture a black hole's singularity, a point of infinite density where gravity becomes quantum. Or rewind to the Big Bang, when the entire universe was smaller than an atom, and quantum fluctuations dictated cosmic fate. In these extreme moments, our best theories crumble, spewing nonsense like infinite probabilities or space-time tearing apart. This isn't just a gap in knowledge, it's a screaming contradiction at the heart of physics. Enter loop quantum gravity, one of the boldest attempts to stitch these worlds together. Imagine space-time not as a smooth fabric, but as a tapestry of tiny, woven loops, a pixelated reality where even the vacuum hums with granular energy. These loops can't be divided further, meaning singularities vanish. No infinities, no tears, just a cosmic mesh flexing under gravity's weight. In this framework, black holes might not end in crushing oblivion but rebound as white holes, spewing out matter in a cosmic encore. The Big Bang, just another bounce in an endless cycle of universes. But there's a catch. Loop quantum gravity struggles to explain why our everyday world looks so smooth, so classical, if space-time is fundamentally choppy. Then there's causal set theory, which strips reality down to its bare bones, a collection of discrete events linked by cause and effect. Think of it as the universe's to-do list. First, a star forms. Then it explodes, then its debris forms planets. No continuous spacetime, just a network of relationships. This elegantly sidesteps infinities by denying them a stage to begin with. But how do we get from this skeletal framework to the lush, 3D world we inhabit? The math is still catching up. String theory, meanwhile, takes the opposite tack. Instead of quantizing gravity, it posits that particles are tiny, vibrating strings whose harmonies dictate the laws of physics. In this symphony, gravity emerges naturally, but at a cost. The theory demands 10 or 11 dimensions, most curled up into knots too small to see. Worse, it predicts a landscape of possible universes, each with different physics, leaving us to wonder why ours is so finely tuned for life. The challenge isn't just technical, it's philosophical. Quantum mechanics deals in probabilities and observations, while general relativity is deterministic, a cosmic clockwork. Reconciling them means answering, what is space-time? Is it a physical thing or a byproduct of deeper relationships? Experiments might hold the key. Gravitational wave detectors could reveal quantum jitters in spacetime itself. Particle colliders might uncover hidden dimensions or gravitons, the hypothetical carriers of quantum gravity. What's at stake isn't just tidying up equations, it's rewriting reality's rulebook. A working theory of quantum gravity wouldn't just explain black holes or the Big Bang. It could unlock time travel, reveal the universe's true shape, or even tell us if there's a before time began. Until then, physicists keep chipping away at the monolith, one paradox at a time, because somewhere in the clash between the infinitely large and the infinitesimally small lies the secret to everything. The moment anything crosses a black hole's event horizon, it's gone, or so we thought. But quantum mechanics throws a wrench into this cosmic vanishing act, insisting that information can never truly be destroyed. So where does it go when swallowed by a black hole? This clash between gravity and quantum rules birthed the black hole information paradox, a puzzle so profound it's forced physicists to rewrite the rulebook of reality. Start with Hawking radiation, Stephen Hawking's bombshell discovery that black holes aren't eternal. Quantum fluctuations near the event horizon cause these cosmic monsters to slowly leak energy, shrinking over eons until they vanish entirely. But here's the problem. That radiation appears random, carrying no trace of what fell in. If the black hole evaporates completely, the information it consumed would be erased from the universe, a direct violation of quantum mechanics' sacred law that information must always be preserved. One radical solution: firewalls. Imagine the event horizon not as a silent point of no return, but a searing wall of energy that shreds anything approaching it. This firewall would encode the infalling information into Hawking radiation, preserving it. But at a horrific cost. It would mean Einstein's smooth spacetime, the bedrock of general relativity, violently fractures at the horizon. Falling into a black hole wouldn't be a quiet descent. It'd be like hitting a cosmic shredder. Then there's holography, the mind-bending idea that all the information swallowed by a black hole isn't lost inside but smeared across its surface, like a 3D movie projected from a 2D screen. The holographic principle suggests that the event horizon acts as a vast hard drive, encoding every atom, every photon that ever crossed it in Planck-sized pixels. When the black hole emits Hawking radiation, it's not random noise, it's a slow, deliberate playback of that data, etched into the radiation's subtle patterns. The stakes couldn't be higher. If information can vanish, our understanding of quantum mechanics, and by extension, reality itself, is fundamentally flawed. But if space-time is holographic, it implies the universe operates like a cosmic computer, with the true laws of physics written in a language we're only beginning to decipher. This isn't just about black holes, it's about whether the universe forgets. And as we peel back the layers of this paradox, we're not just solving a puzzle, we're uncovering the hidden grammar of existence. Imagine a cosmic foam bubbling endlessly in the void, each bubble a universe with its own laws of physics, its own history, its own fate. This isn't science fiction, it's the startling prediction of eternal inflation, a theory that takes the already mind-bending concept of cosmic inflation and stretches it to infinity. According to this idea, the explosive expansion that jump-started our universe wasn't a one-time event. It never stopped. Instead, it's still happening in distant regions of space-time, spawning new universes like soap bubbles in a sink full of dishwater. Our observable cosmos, just one bubble in an endless, frothing sea of realities. What's wild is how this process could work. Picture the inflattened field, the mysterious energy that drove inflation, as a hill with valleys of lower energy. In our region of space, the field rolled down into a valley, releasing energy that slowed inflation and birthed the universe we know. But in other patches, the field might still be perched high on the hill, continuing to inflate at breakneck speeds. Every time a pocket of this field finally tumbles into a valley, inflation ends there, and a new universe crystallizes out of the chaos. Meanwhile, the surrounding space keeps expanding exponentially, ensuring the process never runs out of fuel. The result, an infinite multiverse where universes sprout endlessly, each with its own unique physics. This raises a dizzying question. If inflation is eternal, does causality even have meaning? In our everyday world, cause precedes effect, but in an eternally inflating multiverse, there's no before or after in any absolute sense. Universes bud off from others, but their timelines might be completely disconnected. A universe born today in some distant bubble could have a history that, from our perspective, hasn't even started yet. It's like trying to map the branches of an infinite tree where every twig grows at its own pace, in its own direction. Then there's the anthropic principle, the idea that we observe this particular universe because it's one of the rare bubbles where conditions allow life to exist. Most universes in this foam might be sterile, their physical constants too hostile for atoms or stars. But in an infinite multiverse, even the most improbable outcomes become inevitable somewhere. This could explain why our universe seems so finely tuned for life. We're just in the bubble where the dice rolled in our favor, but how could we ever test such a radical idea? Some theorists look for fingerprints in the cosmic microwave background, subtle patterns or anomalies that might hint at collisions with neighboring bubbles in the cosmic foam. Others simulate the physics of inflattened fields in supercomputers, tracing how bubbles nucleate and grow. The challenge is that these other universes are forever beyond our horizon, their light never reaching us across the ever-expanding gulf. Eternal inflation doesn't just reshape our understanding of the cosmos, it redefines the very meaning of existence. If true, there's no outside, no edge, no ultimate beginning or end. Just an endless dance of creation where universes bloom and fade like sparks in the dark. And somewhere in that infinite froth, we're here in this bubble asking the question, are we alone, or is every possible reality unfolding somewhere in the vast beyond? Consciousness is the one thing we can't seem to explain away. You can break down the brain neuron by neuron, map every synapse, and still nowhere in that circuitry do you find the actual experience of being you. This gap is what philosopher David Chalmers famously called the hard problem of consciousness. But what if the answer isn't locked inside our skulls? What if consciousness isn't something the universe has, but something it is? That's the radical claim of panpsychism, the idea that mind is as fundamental to reality as space, time, or matter. Imagine a universe where even particles have a flicker of inner experience, not thoughts or emotions, but some primal form of awareness. Stars, planets, even the vacuum of space itself might hum with a faint proto-consciousness, like a cosmic background radiation of mind. This isn't just philosophical speculation. Quantum mechanics has long hinted at a strange link between observation and reality. In the double-slit experiment, particles behave differently when measured, as if the act of observation itself shapes their existence. Some interpretations, like the von Neumann-Wigner hypothesis, take this further, suggesting consciousness literally collapses the quantum wave function. Without an observer, reality remains a blur of possibilities. It's a notion that turns the traditional view upside down. Instead of consciousness emerging from complex brains, maybe brains are simply antennas tuning into a universe already saturated with mind. Then there's the anthropic principle, which feels like the universe's most unsettling coincidence. Why do the fundamental constants, the strength of gravity, the mass of electrons, seem perfectly fine-tuned for life? One explanation is the multiverse. In an infinite sea of universes with random parameters, we inevitably find ourselves in the one where conditions allow consciousness to arise. But another, far stranger possibility is that consciousness selects reality. This is the participatory anthropic principle, championed by physicist John Wheeler. In his vision, the universe only takes definite form when observed, meaning we're not just bystanders but co-creators, shaping the cosmos by the mere act of perception. The implications ripple outward. If consciousness is fundamental, artificial intelligence might not just simulate awareness, it could be aware, no matter its substrate. Near-death experiences or reports of cosmic unity during psychedelic trips might hint at a deeper connection between mind and universe. Even the eerie silence of the Fermi Paradox could find new meaning. If consciousness shapes reality, maybe advanced civilizations don't explore space. They dream it, transcending physical limits we can't yet imagine. Of course, skeptics push back. If everything's conscious, why don't rocks write poetry? Panpsychists counter that complexity matters. Just as trillions of water molecules create an ocean's waves, trillions of conscious particles might give rise to human thought. Others argue these ideas are untestable, sliding into metaphysics, yet experiments are probing the edges. Quantum biology explores whether consciousness exploits quantum effects in the brain. Studies on anesthesia aim to pinpoint how it switches off awareness, revealing what physical processes correlate with subjective experience. At the heart of this mystery lies a profound shift in perspective. For centuries, science treated consciousness as an accident, a byproduct of atoms obeying mindless laws. But what if it's the other way around? What if the universe is less a cold machine and more a vast, evolving thought? The edge of infinity might not be a place. It might be the boundary between what we perceive and what's possible when we dare to see reality not as something out there, but as something we're intimately, inseparably part of. And that changes everything. Our journey through the cosmos has been anything but ordinary. We've stood at the event horizon of black holes where time itself stretches and warps. We've wandered through hypothetical wormholes, those cosmic shortcuts that could rewrite our understanding of distance. We've even dared to question whether our reality might be a simulation or one of infinite parallel universes, each with its own version of history. These aren't just thought experiments, they're the bleeding edge of human curiosity, where physics meets philosophy in the most spectacular ways. What makes these ideas so compelling isn't just their strangeness, it's how they change the way we see our place in the universe. Take dark matter and dark energy, those invisible forces shaping the cosmos. We can't see them, yet they make up 95% of everything that exists. That alone should humble us, or consider the possibility that time isn't a straight line but a vast, unchanging block where past, present, and future all coexist. Suddenly, the idea of now feels a lot less solid than we thought, and let's not forget the sheer audacity of human imagination. A century ago, black holes were pure speculation. Now we've photographed one. Quantum entanglement, once dismissed as spooky action at a distance, is now the foundation of cutting-edge technology. Who's to say which of today's wild theories will be tomorrow's breakthroughs? Maybe one day we'll crack the code of consciousness or find evidence of other dimensions. The point is, we're only scratching the surface, but here's the real wonder. The more we learn, the more questions we uncover. Every answer peels back another layer, revealing deeper mysteries. That's not discouragement, it's inspiration. The universe isn't a puzzle to be solved, but a story to be explored, one mind-bending chapter at a time. So keep asking, keep wondering. Share your thoughts in the comments. What theory blows your mind the most? And if you've enjoyed this journey to the edge of infinity, don't forget to like and subscribe for more deep dives into the cosmos. The universe is full of secrets, and the next revelation could be just around the corner. Until then, keep looking up. The stars have a way of putting things